Hello and welcome to section 6.12, where we're going to talk a little bit about equilibrium and reversible and irreversible reaction arrows. You might remember that throughout this course, we have used reaction arrows that in some instances, like for acid-base reactions, have been reversible because of the incomplete ionization of one of the reactants. And at the same time, in one of the past sections here, I used arrows that were irreversible too. When we had this reaction occur. Well, something like this reaction anyway. I think it was a bromide maybe. So what we can say for sure is that if you have a strong reaction that goes completely, such as the bottom one, then you can use irreversible reaction arrows. And if you have something that can happen and then reverse, then you have to use the reversible reaction arrows, which seems like a stupid thing to say, but let's go through each of the four basic types of reaction mechanism and talk a little bit about specifically when reversible reaction arrows might be used. So first, remember, we had nucleophilic attack. So a nucleophilic attack, you can actually have cases where you use irreversible reaction arrows or reversible reaction arrows, depending. So if you have a case where you have a not so great nucleophile, such as water, and it's attacking something like, let's say, this ketone, this carbon double bonded to an oxygen, you can have nucleophilic attack using nucleophilic attack arrows starting from the lone pair ending at the electrophilic carbon, which would normally violate the octet, but we send the electrons right up to the oxygen. And the molecule that you end up forming is actually not very stable because oxygen with two substituents and a positive charge is not, or is a very good leaving group. So because of that, you can actually have the reverse reaction occur, and there's some equilibrium between the products and reactions here in this shown reaction. However, if the nucleophilic attack ends up forming a stable compound, like let's say instead this was a negatively charged carbon plus a ketone, then what can happen is the reaction nucleophilic attack arrows can start at the lone pair end at the electrophilic carbon. The electrons kick up to the oxygen, forming irreversibly this negatively charged oxygen species, tert butoxide. So in nucleophilic attack terms, these are when you would typically use two different types of arrows. In the loss of a leaving group sense, you can also have an instance where you need to use either reversible or irreversible arrows because you can have things that when they leave are also good nucleophiles. So if you have a molecule like this, And the leaving group leaving creates, say, a positively charged species and a good nucleophile like iodide, then the iodide is such a good nucleophile that it will just be happy to just turn around and attack that carbocation again to reform the reactants. But hopefully, if you have a molecule, oh, this should be, let's change this here. Let's move all this down. Let's move all this down here. There we are. And then we can write in here, loss of a leaving group. There we are. Very nice. Okay, if we instead have a leaving group that is not a very good nucleophile, then things certainly change. And the type of a type of poorly nucleophilic leaving group can be found in our previous example, where perhaps we have this molecule that has the water leaving again, to give us our ketone back plus water. This is definitely reversible, or this is we're going to say irreversible, or no, this one is also reversible, sorry. This one is reversible. However, if we were to change the structure of our reactants in such a way that it wasn't reversible, then we would do so. But in this case, these are both reversible. And in fact, loss of a leaving group is most often reversible because you're making some positively charged center, and the leaving group often has a negative charge there too. Right, so that's mostly reversible then. So then for the third type of reaction that we had, it was the proton transfer reaction. And we've talked at length in several different sections about how the proton transfer reactions are mostly reversible. There are cases when you can have irreversible proton transfers, such as, let's say that you have a huge pKa difference, like this butyl lithium molecule. If you react this with water, for instance, the proton transfer happens like this, where the butyl lithium takes one of the protons and it is transferred from the water to the butyl lithium to give us now that's just butane plus lithium hydroxide. And this is irreversible because the pKa of butyl lithium or a butane is like 45 and water is 16. So that difference of 29 units is big enough that you don't see any reversible behavior, basically. Right, so that takes care of proton transfer. And last, we have number 4, which is carbocation rearrangements. And here, actually, carbocation rearrangements only occur if there is if the following molecule, the product, will be more stable. And because of that, each of the reaction arrows are actually irreversible. So if you have a methyl shift, it happens irreversibly. to give you the secondary cation from the primary. And this has been section 6.12.